So we left off last week looking at unit circle trig and looked at 6 different formulas, which might be good to review. Yep. And does anybody remember when we want to find the sine, we need part of the coordinate to do it? Does anybody remember what part? That was the y. And the cosine was the x. And what about the tangent? Y over x. Now there were 3 other trig functions. Does anybody remember the name of the one that we wrote across from sine? And what did you do to the y?
You put it under 1.
Yeah, you flip it. Okay, you flip it. And how about the trig function that you flip when you flip cosine? What's that one? So that's secant. And what was the formula for that? 1 over x. And the name you get when you take the tangent and flip it? Cotangent.
And that's just x over y.
And that's x over y. So those are the 6 formulas that we use when we do unit circle trig. And they are all dependent on finding the coordinate for an angle. So we talked about how to get 4 coordinates last time. 0, 90, 180, and 270. And this is on a unit circle. So what was the coordinate for 0 degrees?
1, 0.
That's the coordinate for 90. Oh, wait a minute, no. 1, 0. Yeah, that's 0.
Okay, I thought I forgot how to read branches.
How about 90? 0, 1. And 180? So it's negative 1, 0. And 270?
0.
So knowing those 4 coordinates, we can find the sine, cosine, tangent, cosecant, secant, or cotangent for those 4 angles. What we're going to look at today is how we can do multiples of 30s and 45s. So 45 would be right there, a 30 would be right there, and a 60 would be right there. And if we can do the 30, 45, and 60 in the first quadrant, then we can do them really in any other quadrant, because it turns into a mirror image of the coordinate. All right, so let's take a look at what we're going to do. So we're going to try to find the 6 trig functions for the angles 30, 60, and 45. Then we're going to look at multiples of those angles. And the last thing, which they start to talk about a little bit in this section, because I can kind of tie it in with what we're doing, is a little bit with what's called trig identities. We're not going to spend a lot of time on this. We're gonna do this much later, probably in maybe chapter 7, where we spend a couple days on it. But they just kind of start to introduce it here because it is connected to these formulas that we just wrote down on the other page. And I'll show you how. All right, so let's start with a 45-degree angle and see how we could get the coordinates for it. So if you have a 45-degree angle on the circle, it's exactly halfway between 0 and 90. And what we're going to do is kind of make a triangle out of it. Now, this is on a unit circle. So how long is the hypotenuse in that triangle? 1. Unfortunately, that doesn't really give us the coordinate, because the coordinate is not when you move on a diagonal. The coordinate is when you move right and then up. So we don't know how much right and how much up we go. But if you compare how much right and how much up, how would the 2 numbers compare? Yeah, they'd be the same, because this is an isosceles triangle. We know this is a 45-degree angle, because that's how much we rotated the hypotenuse to point at 45. And if that's 45 and that's 90, they all have to add up to 180. So any questions on why that's a 45, 45, 90 right triangle. Okay, so let's draw the same thing, just a little bigger, so we can work with it down here. So we know that side is 1. And I don't know the other two sides, but they are the same. So I'm going to pick a variable. Let's call the base x. What does that mean the height would be?
X.
Would also be x. So we have one variable we need to solve for it. Anybody have a guess what formula we could use that relates all the sides in this triangle? What's that? Pythagorean theorem. Can somebody tell me how I would apply Pythagorean theorem to the values I have in that picture?
X squared plus x squared equals 1 squared.
Yep. X squared plus x squared equals 1 squared. And now, solve for x. Okay, so what's x squared plus x squared?
X. 2x squared. Yeah.
2x squared. How about Christian? What's the next thing I would do here to get x by itself? Yep. Divide by 2. Divide by 2. So now we have x squared equals a half. And Logan, how would I get x by itself to get rid of that exponent? Yep. Take the square root of each side. So remember, when you square root a fraction, just do the top and the bottom separate. Well, the top comes out nice. So that's the square. That's 1 over the square root of 2. But what's wrong with that? Yeah, we don't want to leave that radical. So what can you multiply top and bottom by to fix that? Square root of 2. So square root of 2 over square root of 2. And what would that give me? Square root of 2 over 2. So now we know what x is. It's the square root of 2 over 2. Yeah.
I mean, obviously that's for a unit circle, it's going to be the same every time. But could we just use the 45, 45, 90, and the 30, 60, 90 triangle here?
If you know that, you would be able to use that as well. Yep. So we know that the base is square root 2 over 2, and we know the height is square root 2 over 2. So now apply those two numbers to the triangle in that circle. What would be the coordinate for 45 degrees? Where'd you get that number?
2 over square. Oh, the square root of 2 over 2.
Yeah. So square root of 2 over 2, comma.
Square root of 2 over 2.
You go right root 2 over 2, and then you go up root 2 over 2. That's the coordinate for 45 degrees.
Yeah, I think we solved the side tangent formulas for that.
Yep. That's one I put on the board. I think it was the problem. I said do 1, 5, and 8, and then I gave like 3 other ones at the end, and that was one of them. We didn't know at the time that it was a coordinate for 45 degrees, but now we do. So that's your coordinate, and that's always the coordinate for 45 degrees. You do need to know the coordinate. Okay, so that's something you'll have to memorize. Now, we're not quite here yet, but 135 is over here. What do you think the coordinate for 135 is? Yeah?
You have square root of 2 over 2, and then square root of 2 over 2.
Right. If you know the coordinate in quadrant 1, you can do the 45 in any quadrant because it's just a mirror image of that triangle. It's always root 2 over 2 and root 2 over 2. This is sometimes they're positive, negative, or one of each. We're just going to focus on quadrant 1 right now. Okay. Any questions on how we got that coordinate? Okay. So let's take a look at the 30, 60, 90. All right, so this time you'd have your unit circle, and 30 be about right there. And we're going to do the same thing. We're going to make a triangle, and the goal is to figure out the base and the height. So there's your hypotenuse. And what would be the length of that? That we know is 1. Again, it doesn't really help us directly to give us a number for the coordinate, but it will help us. You've got your height and your base. So now this is a 30. What about the angle up at the top? That's a 60. So can I do the same trick that I did last time and use Pythagorean theorem?
No, it's the other two.
Right, the other two sides aren't equal. So if I was going to label these with variables, one would have to be x, one would have to be y. And then when I try to solve that with Pythagorean theorem, I get x squared plus y squared equals 1 squared. The problem is that's two variables. I can't solve that. So we're going to have to use Pythagorean theorem, but we've got to figure out one of these other variables a different way first. And I know this is 1. So this is my hint. Okay, let's go like that. And let's go like that. So any thoughts how we're going to figure out the x or the y? Yep.
You use trig functions.
If we knew like the trig, like you mean opposite, adjacent, and hypotenuse kind of stuff. If we knew right triangle trig, or we could do that, let's try to do it without that. Because we haven't learned that yet, and there is a much simpler way to do it if you're clever.
You like combine two triangles to make it easier for you.
Okay, how could I combine these two triangles?
Flip it horizontally. Flip it horizontally and add them to two lines together. I don't know.
Oh, if you're rectangle.
Flip it horizontally.
I don't know. And then I don't know if that be an isosceles.
Let's see. So you put it on.
Make a try.
Well, it would be isosceles.
I don't know.
But I'm not sure what to do with that.
Yeah, okay, I don't know.
I'm looking for. I still want to make another type of another shape, but not isosceles.
Oh, wait, no, you make a square.
You could make a rectangle out of it. I'd still kind of be in the same situation. I wouldn't know what to do with that. Anyone have another idea of something? Yeah.
Could you correspond the angles with the sides?
Okay. What do you want me to do with? Let me put it back the way it was. We do want to make another shape. So how are you saying to do it?
So you could flip it, and then you could line up the lines together, and then you would realize that the 30 degrees would be smaller than the 60 degree side. So the 60 degree side would be 2x, and then the 30 degree side would be x.
So how would you flip this? Because that's what Nate said. He said flip it. And I did that already. But what are you saying that's different?
Would you have to flip it vertically and horizontally?
If you do it that way, I think you could try to make a rectangle. But let's just do the first thing you said. Just flip it vertically. So what could I do now? Yep.
Oh, I'm not sure how you would or you were thinking about overlap them. Overlap them so the side across from the 30 degree angle, both of those sides are completely overlap.
Make it 60-60 triangle.
Just make it equilateral.
Like that?
Yeah. I know.
Well, that's an interesting shape. But I'm not sure what to do there, yeah?
Yeah, you can make an equilateral.
Right, we can make an equilateral triangle.
So close. Except I didn't do it at all.
So now we've just created a triangle where all the angles are 60, 60, and 60. So what does equilateral mean?
all
Same
side.
length side. Right. Same side.
Right.
It's equilateral.
Angular is different.
Same thing.
Triangular. Oh.
So we know that in equilateral, all the sides are the same. So we know this side is 1, this side is 1, but more importantly, that side is 1. And what do we know about this part and this part? They're equal. They have to be because they're mirror images of each other. So that now tells you that this top part is how long? 1/2. And the bottom part is 1/2. So if you're clever with making that, you can figure out pretty easily how long each side is, and you don't have to use anything fancy to do it, just by creating a mirror image of it. Is there any question why each of these is 1/2? Okay, so now we don't need the bottom triangle anymore, because we know 2 out of the 3 sides. We can go back to the Pythagorean theorem and get the third side. So just to simplify it, I'm just going to move that away now. So 1/2, and let's call that side x. So how would I set up Pythagorean theorem to find x? Yeah?
X squared plus 1/2 squared equals x squared. 1 squared.
1 squared. Right, so x squared plus, what's 1/2 squared? 1/4. So x squared would equal how much? 3/4. So x would equal? Yeah, what do we get when we simplify that? Square root of 3/2. So there's your x value. So we've got the x and we've got the y, so now we can write down the coordinate. So what would be your coordinate for 30 degrees? How far over do you go? Square root of 3/2. And then, how far up? 1/2. And that is always your coordinate for 30 degrees. Root 3/2, comma, 1/2. If you forget which number goes where, well, square root of 3/2, if you divide that out, is about 0.87. That's a bigger number than 1/2. 1/2 is 0.5. So the bigger angle always goes across from the bigger number, and the smaller angle goes across from the smaller number. Right, now let's look at 60. So for 60, we don't really have to do that much work. So 60 degrees is 30 degrees to the right of 90. Okay, here's 90. So this angle now is 90. This angle is 60. And what about the angle at the top? 30. So it's exactly the same triangle I just had. The only difference is it's been kind of like reflected and then turned on its short side. So I want to know how far over, and then how far up. So what do you think the coordinate for 60 is?
One more time.
What is it?
Would it? Oh wait, no, it'd be 1/2, then square root of 3/2.
Yeah, 1/2 square root 3/2. Because now the side across from the 30, that's your short side. And the short side, or the side across from the 30, is always your 1/2. And the long side is what's across from your 60, and that's your root 3/2. Any questions on the coordinate for 30 or 60? All right, so now we could do something like this one. That would be 150. What do you think the coordinate for 150 would be?
Negative 3 over 2, 1 half.
Negative square root 3 over 2, 1 half. So knowing the 30s, the 30, the 45, and the 60, that allows you to do the 30, 45, and 60 in quadrants 1, 2, 3, and 4. So that gives you 12 different points that we can find the coordinate for, or 12 different angles you can find the coordinate for. And then we also have the 0, 90, 180, and 270. So that essentially gives you 16 angles you should be able to find the coordinate for. And if you look at it, 30, 60, and 90, when you graph them, if I try to do a pretty good job, there's your 45, there's your 30, and there's your 60. If you notice, they are not spaced equally throughout the quadrant. They're kind of centered in the middle. Same thing here. That's because we're missing the 15s. This would be 45. 60 and 45 are only 15 apart. 45 and 30 are only 15 apart. So the next one would be right here. That would be 15, and that would be 75. If we did the 15 and the 75, then you would have points that are all equally spaced. But we kind of have 3 points that are kind of grouped in the center of the quadrant. And that's the only ones we're going to do for now. Okay, so 3 coordinates you have to remember. Root 2 over 2, root 2 over 2. That's your 45. Root 3 over 2, 1 half. That's your 30. And 1 half root 3 over 2 is your 60. And I always just kind of try to visualize it in my head. And that's how I figure out which side is which. All right, so let's try some questions. So, find the 6 trig functions of 45 degrees. All right, so to use unit circle trig to do that, what's the first thing you need to know? The what? You've got to have the coordinate. Unit circle depends on an x and a y. So rather than go through and calculate it all over again, we just want to memorize it. Yep. Root 2 over 2. Root 2 over 2. And we reviewed our formulas earlier, so let's start with sine. What's the sine?
Root 2 over 2.
And which one? Just
the y.
It's specifically the y. Yep. There's your sine. What about your cosine?
Root 2 over 2 with the x.
And this time it's the x. And what about your tangent?
2 over 2 over root 2 over 2 or y over x.
And what do we get when we divide that?
We need to simplify that.
Yep.
That I can
Is that like 2 root 2 over 2 or no?
Well, you're dividing y and x, right?
Oh wait, wouldn't it just be one because you're dividing something by itself?
Y and x are the same thing. Yep.
Never mind, I was even.
So yeah, don't overthink it, right? So you don't have to really do anything fancy there. It's just 1. So let's do the cotangent while we're right here. What's the cotangent going to be?
That'd be
1. Remember, you take your tangent and you flip it, and that gives you your cotangent. And I just did that one because that one's the easiest one. Now, let's do the cosecant. What's the first step to get the cosecant? Flip what? Sine.
Yeah.
So let's flip the sine, okay? And anytime we end up with a root in the bottom, we just need to fix it automatically. So what does 2 over root 2 turn into? Square root of 2. Yep.
Wait, why? Oh, because it'd be 2 times square root of 2 over 2.
Yep. And what about your secant? It's the same thing because the sine and the cosine are the same. So you've done that problem. We did it last week. The only difference is I gave you the coordinate. You didn't know, or I didn't teach you, it was the coordinate of 45 degrees. Questions on? Alright, so there's your 45. Let's try a 30. So 30 and 60 is a little trickier because you gotta get them right. You can't flip the 1/2 and the root 3 over 2. So what I do in my head is I kind of imagine where 30 would be. I know that 30 is lower on the circle than 60. And then I imagine the triangle. This is the long side. That's the short side when you draw a 30. The short side is always what number? That's always your 1/2. And the long side is your? That's your root 3 over 2. So now I know the coordinate is root 3 over 2 is the x, 1/2 is the y. Okay, 3 over 2 is the x. There we go. And now from here, it's just plugging them in. So let's start with sine. How about Savannah? What's my sine?
I'm just trying to find which sign is what, the x or the y.
Sine is the y.
The y?
Yep.
1/2.
That's your 1/2. There's my sine. Christian, how about my cosine?
Square root 3 over 2.
Square root of 3 over 2. And what's the formula for tangent again?
Y over x.
Tangent is y over x. And this actually kind of relates to the last thing we're going to do. But what's y? Well, in general, y is the what trig function?
Sine.
Yeah, sine. And x is the cosine. So really, tangent is sine over cosine. That's an example of an identity. The tangent is the sine over the cosine. So what I imagine here is just put a dotted line right there and divide the sine by the cosine, and there's your tangent. Now, when you divide two things with the same denominator, what happens to it? It cancels because you would flip and multiply. So all you end up with is 1 divided by square root of 3. And what does 1 divided by square root of 3 turn into?
Square root of 3 over 3.
Yep, square root of 3 over 3. All right, my cosecant. How about maths? What's my cosecant?
Cosecant?
Yeah.
Isn't it 2 over 1, which is just 2?
Yep, it's 2. How about my secant final answer? All fixed, yep.
2 square root of 3 over 3?
Yes, 2 square root of 3 over 3. Is there any question on that? Now, to get the cotangent, you can make life easier or harder. You could flip either what's circled in black or what's circled in red. They're the same thing. That's why they're equal.
Easier to circle than the rest.
Flip the one that's in the red, because then you're done. If you flip the one that's in the black, you're going to put the root back in the bottom, and then you have to fix it all over again. And there's your 6 trig functions for 30. Questions on those? Now, what's the difference between a 30 and a 60 in terms of the coordinate?
30 has, well, 60 is 30, but flip around.
Right, the x and the y just switch places. So when you do the 6 trig functions of 60, you should expect all the same answers that you just got for 30, except everywhere there was an x, that becomes a y, and y becomes an x. So they're all going to switch places. So first of all, this is 180 divided by 3, which is 60. And what's the coordinate for 60? Let's see if we can just visualize it. Think about it.
1/2 is x.
Yeah.
Square root of 3 of, no, but wait. I don't know.
Square root of 3 over 2.
Oh, that was a lot.
So 1/2, because 60 is more towards the top of the circle. So now the short side is on the bottom, and the tall side is going up. So 1/2 root 3 over 2. And let's go through the 6 functions. What's our sine? root 3 over 2. What about the cosine? 1/2. And remember, if you think about it as an identity, tangent is sine over cosine. So just imagine dividing those. What's your tangent?
Root 3 over 1. Oh, yes.
Yeah, root 3 over 1, which is just root 3. Okay, how about your cosecant?
Oh, wait, no.
2 root 3 over 3, right? You just take that and flip it. How about our secant? 2. And what about the cotangent? If you're not sure if that's a fraction, just think of it that way. Square root of 3 divided by 3. Any questions on how we got any of those values? Is that important for calculus, Mr. Babb, or not really?
Have I not done the disclaimer in this class yet?
I don't know.
How this stuff is very important.
I would say, yeah, I would say this is like this is one of those things that just ruins some of my calculus students every year.
I mean, even if it takes you a second, because you don't have it memorized, at least if you can think of it, circle, coordinate, yep, okay, got it. It takes you a second to get it. But the idea is to try to memorize those coordinates so you can figure them out.
I actually don't use the coordinates, Mr. Hager.
Oh, you don't?
I use special right triangles.
Yeah. So yeah, you can do it. There's different ways to think about it, kind of organize it in your head. But as long as you've got a way to get it, that's what's important.
Do you want me to show you the special right triangle method?
Maybe at some point, yes.
He doesn't want me to show you right now.
No.
You don't have time? You never have time, Mr. Hager.
How about 135?
Okay.
What's your coordinate for that?
Oh, okay. I thought you were talking about a time.
So if you get stuck, think through, is this a multiple of 30 or a multiple of 45?
30. No, 45.
Yeah, multiples of 30 have to end in 0.
Yeah, that's what I meant.
So multiples of 45 that are in the middle of a quadrant always end in a 5.
Yep.
So it's a multiple of 45. Where on, like, which quadrant? Which one?
The top left.
Which one is that? That's 2. So we're talking about a 45 in quadrant 2. So how long is each side on the 45, 45, 90?
Root 2 over 2.
They're both root 2 over 2. But when you think of your coordinate, just be careful when you write it.
That's negative root 2 over 2.
Comma.
Yeah, and then positive.
Positive. And they're only having us do the first 3 this time. So what's your sign?
Root 2 over 2.
The y, which is?
Root 2 over 2.
Yeah, root 2 over 2. Your cosine?
The x, so negative root 2 over 2.
Negative root 2 over 2. And what about your tangent?
Negative 1. Just negative 1.
Just negative 1. Just when you divide them, they're opposites. So you get negative 1. Would any of those come out undefined if you flip them?
Yeah, the cosine, because it's a negative.
So negatives cause things to become undefined when you flip them?
Negative square root in the denominator, right? Doesn't that make it? Doesn't that ruin it?
You shouldn't have it.
No.
Oh, then no.
What would be a problem that would cause undefined? 0.
So you can't have radicals.
Multiples of 30 and 45 that are within the quadrant are never undefined. The only ones that can be undefined are the ones that are on an axis. 0, 90, 180, 27. We already went over those. Yep. All right. How about this one?
Oh, shoot.
If you're having trouble, what might it be easy to do in your head first? Like if you have trouble thinking about it like this. And you could make it degrees. What is that in degrees? Well, think about pi over 6. What's that?
It's
Oh, it's 30.
It's 30. But this is 7 pi over 6.
It's 210.
So it's 210.
That's really
And now think about 210. Is that a multiple of 30 or 45?
30.
That's a 30. So we're going to involve the 1/2 and the root 3 over 2. So think about where 210 is. Where's 210 on the circle?
Quadrant 3.
Can you give me kind of where in the quadrant?
Bottom left.
Well, like,
Oh, sorry.
let's say closer to the x-axis, the y-axis, or right in the middle.
Closer to the X.
Closer to the x. So there's your triangle.
So it'd be 31.
So what's your coordinate?
Negative square root of 3 over 2.
Yep.
And then negative 1/2.
So it's negative, negative, because you're in quadrant 3, and the long side is your horizontal, and the short side is your vertical. So what would be your sign? Negative 1/2. Good. Your cosine?
Negative 3 over 2.
Negative root 3 over 2. And your tangent?
Root 3 over 3.
So yeah, when you divide them, the negatives are gone. And if you're not sure how they got that, you end up with 1 over square root of 3. But what do you get when you fix it?
Is it negative?
Nope, it's positive because it's a negative divided by a negative.
Root 3 over 3.
So root 3 over 3. Okay, so this is a good time to ask some questions on this because from here we start doing them like faster. But is there any questions on how we're getting these values?
It's easy now, but I don't know what will happen when I get home.
So eventually, if you memorize them, like if you just know, like, you know, sine 45, root 2 over 2, if you just memorize them, that becomes really fast. But at least if you can figure it out, that's a good thing. Yeah.
How do you know what the coordinates are?
We proved them. We proved them with Pythagorean theorem, and so we derived them.
We draw a circle and it all works out.
Yeah, that's kind of it.
So the hope is now you don't have to go through and derive them with Pythagorean theorem and all that all over again. Okay, you want to just definitely want to memorize the coordinates. Okay. Is there any other questions on that? Now, I said technically there are 2 other angles that we could do, but we're not doing them yet. And those ones were multiples of what number? 15s. So we can do the multiples of 15s, which we'll get to. But we need a trig identity to do that. And we're going to talk a little bit about trig identities today, but not the one you would need to do that.
Is that the term that you just used a second ago to say that tangent is equal to sine over cosine?
Yep.
Is identity?
That's an identity, yep. This is the 15 multiple thing, that's a different identity.
Yeah.
So what do we do if we have to find a trig function that's not a 30 or 45? Like if we had to evaluate the sine of 42 degrees. We use the calculator.
Oh, okay.
Yeah.
42 degrees is not one you're easily going to be able to find, if at all, an exact coordinate for it. I don't know how you'd find an exact coordinate.
You might just do like an inconsistency.
You can only find exact coordinates if you have things that are like multiples of 15. You could do 7.5. You could do halves of things, but 42 isn't really half of a nice number that we know. It's not double a nice number that we know.
You have to do multiple different halves of different angles to somehow get like 100 degrees.
Yeah, you wouldn't be doing this on the unit circle. Just not. So let's go through how we do it. Make sure you guys know what we do on the calculator. Alright, what do you think the first thing I want to check on my calculator is?
Where the sign button is.
Okay, you need to know where the sign button is. Something else I should check first. Yeah?
Is it degrees?
Right, because some problems are going to be in degrees. Other problems are going to be in, I thought I had one in radians. Yeah, radians. And how do you know that this problem is in radians? Degree sign, right? Radians is actually, that's more common. Radians is what you'll use more of in calculus, I would say.
I would say degrees are useless and you should only use radians.
So, there you go.
No.
So first thing is check to make sure we're in the right mode. Okay, so go to your mode. For this problem, I'm in the wrong mode. So I'm going to do degrees. And I change it to degrees. How would I type in the first one?
Sign button.
Yeah, sign button, and then 42, close it, and there's your answer. I'll just drag this to the screen so you can see it.
How come yours gets rid of the 0 before the decimal point? Is that like a setting that you have?
Maybe. I think most of them don't have the 0. Am I correct?
Yes.
Yeah, maybe yours is different.
Okay, yeah. Yeah.
How about the next one? How would I type that in? Just cosine 42. All right, and the last one. Tangent 42. Okay. So those are the only 3 that we have buttons for directly. We can still do the cosecant, secant, and the cotangent. We do it exactly the same way we would do in unit circle. What would we do with this value to get the cosecant?
1 over.
Which basically means to do what? Flip it. So if you want to do the cosecant on the calculator, you take the sign and you flip it. There you go. I would use the exact answer. I would round that and flip it. Just type it in like I just did. How would you type in secant? Flip the cosine. And how would you type in cotangent? Flip the tangent. If you're thinking, well, what about those -1 things up above it? Like sine to the -1, cosine to the -1. That's inverse trig. That is something we'll talk about. But not with this. We'll talk about that when we do right triangles. So there's your 6 trig functions. Any questions on how we found this?
Are we writing those down?
Well, you gotta make sure you know how to do it, on a test or on your calculator. Okay. So this one's just asking for 2, the sine and the cosine. Yeah.
Just real quick, how do you switch from radians to degrees again?
We might have to talk about that right now. Okay. So what's the first thing I should check here? Right, I should check what mode I'm in. And right now I'm in degrees, but this problem is in radians. It's not going to say to you on the test, now change your mode to radians and type it in. It's just going to give you a problem and you need to know it's not degrees. Okay, so mode, and then it's the 4th option down. Hit enter on radians, and it should say radians at the top. And then from there we type it in just like usual. Sine of 10, cosine of 10. There's your 2 answers for this one. As far as rounding, we're generally going to round to 2 decimal places, maybe 3. If you're doing anything other than a multiple of 30 or 45, rounding is always done. Any questions on that? So that's the main idea of unit circle trig. So now you should be able to figure out the coordinates for any of these points. There's your 30, your 45, and your 60 in each quadrant. Remember, the 30s and 60s involve the 1/2 root 3 over 2. What does the 45 coordinate have as its number?
Root 2 over 2.
That's the root 2 over 2. And last week, we did the 0, 90, 180, and 270. So there's 16 different points. And each point has 6 trig functions I could ask you about. Any questions on that? All right, so what did we say? Let's go back to this again. When you have sine, what do you do with it to get cosecant? You flip it. Now, do you only flip it if you're doing pi over 3, or would it work no matter what you're trying to find the sine of? Like, this is 60. Can you only find the cosecant of 60 by flipping the sine of 60? Like, could you do 58 if you wanted?
I don't think so. Why would you? That's a different number.
Right, but my question is, could you still flip the sine of 58 to get the cosecant of 58?
Yes.
Could you flip the sine of 12 to get the cosecant of 12?
Yes.
Yeah, it works all the time. When you have a formula that works all the time, no matter what you fill in, that's an identity. So those last few problems we did, we saw a connection between sine and cosecant, cosine and secant, tangent and cotangent. And the connection was you flipped one to get the other. What's that called? Reciprocals, exactly. So these are what we call reciprocal identities. Reciprocal because you flip them. Identity because it's always true. And you can think of it two different ways. If you take the sine and flip it, you get the cosecant. But if you take the cosecant and flip it, you get the sine back. How about if you flip the cosine? What does that give you? That gives you the secant. Now, what do you think would happen if you flip the secant? That would give you the cosine. These two are not different identities. They're the same identity rearranged. It's kind of like saying, I don't know, distance equals rate times time. And then you just take that formula and just write it different ways. Distance over rate equals time. How else could you say? Distance over time equals rate. This is basically what we're doing right now. All you're doing is switching two things. So they're the same formula. How about, what do you get when you flip the tangent? Cotangent. What if you flip the cotangent? You get the tangent. Okay. And those are all called reciprocal identities. And as far as on a calculator, that is the only way you can type in the cosecant, the secant, and the cotangent. You have to take one of the three that we have a button for and flip. All right, so let's look at a couple special properties about sine and cosine. And the easiest way to show you this property is going to be to look at the graph. And this is also a good connection with what we're going to do tomorrow. So I'm going to type in sine. This is going to be the first time that I've shown you what the graph of sine looks like. Does anybody know what it looks like? Yep, it's a wave.
Whoa.
There's the graph of sine. And the graph of cosine is similar. Could anyone describe the difference between the two? Maybe in terms of like a transformation?
It was shifted to the right.
Yeah, whichever way you're thinking of it. One of them is a shift left to right.
Yeah, sorry.
It's actually a shift of 90 degrees. When we talk about shifting left and right in trig, we call it a phase shift. But just a fancy way of saying it's a horizontal shift. So they have a pretty limited range. What does it look like the range is for both sine and cosine? Yeah? 1 is the highest, and -1 is the lowest. They don't go above 1 and -1. Could you stretch them to do that? Sure. You could do a vertical stretch and then it would. But the normal ones go from 1 to -1. And how about left and right? How far do you think these graphs go? Forever. So when you're talking about sine and cosine, your domain is all real numbers. So it's everything. But the range is very limited. It's only -1 to 1. And we talked about when we did unit circle trig, maybe an angle like like this. 810 degrees. That's a little hard to think about the coordinate because it's such a big number. What did we say you can do to an angle to make it smaller to work with and it won't affect the coordinate?
Add or subtract 360.
We could add or subtract 360. So if we take 810 and we subtract 360, we get 450. Well, to me, that's still kind of a big number to think about. So what could I do? Subtract again. It's just 90. So that's the sine of 90 degrees. And now we could find the coordinate and do whatever we want. So you can add or subtract what again? 360, or in radians, that is 2 pi. So if you take the sine of an angle, or the sine of an angle plus any multiple of 2 pi, it will come out exactly the same. Again, n is just an integer for how many times you've added 2 pi. And if you think, well, you didn't write subtract here, well, you could have a negative integer. So adding or subtracting multiples of 2 pi to any value will not affect the sine and cosine. Now that's not necessarily true with tangent and cotangent. We'll talk about those. It's a little different what the period is there. But for sine and cosine, adding and subtracting 2 pi would look identical. Now, this is not a proof, but I could do an example, sine of x, and then sine of x plus 2 pi. Hi, Mr. Babb. Have a great day.
I left a formulation for the sine of 42 on your desk. It's really bad.
Oh, is it an exact answer?
No.
Oh.
Because it's not possible, but it's really gross. You have to use like multiple versions. I got it down to like 4 versions of the form, the identity you were referencing.
Yeah,
It's not nice.
Not nice. So there's sine of x, and there's sine of x plus 2 pi. How do they compare? They look the same. And if I added 4 pi, it would look the same. 6 pi, 8 pi, 10 pi, any multiple of 2 pi, and it would look exactly the same. We usually use that trick when we have to do unit circle and we want to get an angle between 0 and 360, so it's easier to see. And this property is called the periodic property for sine and cosine. We're going to learn that trig graphs are what we call periodic because they repeat themselves over and over and over. It's not like a parabola. If you think of a parabola, it doesn't keep repeating itself like that. Parabolas don't do that. There's one parabola and then you're done. But the sine and cosine keep getting a wave that repeats. And that's called the periodic type of function. All the trig functions that we've studied so far, all 6 of them, they are all periodic. But they do not all look like waves. Okay, we're not going to look at the graph of the tangent today. We're going to look at sine and cosine a lot more tomorrow. So I'm going to write down a couple more identities about trig functions, besides just the reciprocal ones. And remember that an identity means it's a formula that's true all of the time. It's not a formula that works some of the time. So you could think of like circumference equals 2 pi. That's an identity. The circumference always equals 2 times pi times the radius. It's not like that formula only works if the radius is 7. It works for everything. Okay, so an identity is a formula or an equation that is true for all values. Okay, so the first group of fundamental trig identities are the reciprocal ones. You could just write reciprocal because you already have all the reciprocal ones written down. We already did that. The next group are what we call the tangent and cotangent identities. And I already talked about these. When I said to you, when you want to think about tangent, think about it as dividing what by what? Exactly. Tangent is always equal to sine over cosine. Well, if tangent is always equal to sine over cosine, then cotangent must be cosine over sine, because you flip one to get the other. So that's a way you could figure out the tangent, like if you had a calculator and the tangent button didn't work, but the sine and the cosine button did, no problem. You can figure out everything you need to with just sine and cosine and trig. You don't actually need the tangent or the cotangent button. It makes it faster. Right, and there is one more group of what we call fundamental identities. I'm not going to put them down right now. They're called the Pythagorean identities, but we're not. I don't want to go through those right now. So. And here's an example. Like there's 2, and there's 6, so there's 8 different identities. There's thousands, tons of them. And the idea is when you're doing something in calc, you usually have a table. Sometimes it's on the inside cover of the book, front or the back cover, and you look up the identity that you need to use. Because beyond the fundamental ones, it's really hard to memorize all of them. It's too many. So you see a formula, and you look at your book, and you find the one that you need from a reference table. That's how you work with identities, except the basic. So you would definitely want to know these. All right, I'm not going to do that. All right, so let's look at an example like this. Here's a problem where I want to simplify the cosecant times the tangent. Cosecant of what? Of anything. I don't know. I just want to come up with a formula that would take the cosecant of an angle, multiply it by the tangent, but do it all in one step. Think about cosecant for a second. What was our formula for cosecant using a reciprocal identity?
1 over sine.
It's 1 over the sine. And what's our formula for tangent? Thinking about that using sine and cosine. It's the sine times cosine. And now when you're multiplying 2 fractions, and you have the same thing in the top and the bottom, cancels out. So now we end up with 1 over cosine. And look back at your reciprocal identity. What do you get when you take the cosine and flip it? You get the secant. So a shorter way to take the cosecant of something and multiply by the tangent of it is just to take the secant of it, and you get the same result. This is an example of a trig identity. This isn't one I would know off the top of my head. Like if you said what's secant times tangent, I wouldn't know. It'd take me about 5-10 seconds, and I could quickly do it and tell you what it is. Any question on that? We're going to spend a lot more time on these. Let's try, I think I got 2 more. Let's try the secant times the cosine. And the trick here, in case you're, well, how did you do that last one? Try changing it all to sines and cosines. That's the trick. Start with secant.
Oh, I see what you did. My bad.
How can we change secant?
1 over cosine.
So that's 1 over cosine. Well, the other one already is cosine, so just leave it like that. So what do you get?
Just 1.
Just 1. If you take the secant of an angle and you multiply by the cosine, you always get 1. Well, yeah, of course, because remember, these are reciprocals. If you take something and you multiply by its reciprocal, what do you always get? You always get 1. So in this case, it just comes out to 1. And let's look at this one. Cotangent divided by cosecant. So let's think of what cotangent is first.
That's just
Think of it as a fraction.
cosine.
It's cosine over sine. Now somebody else might be saying, well, how come it's not 1 over tangent? It is, but for this, it helps to write it with sine and cosine. So it's cosine over sine divided by
1 over sine.
1 over sine. So how do you divide a fraction by a fraction? You multiply by the reciprocal.
Also, it's just cosine.
So cosine over sine times sine over 1. And what do you end up with?
Just cosine.
Cosine. So the point to this kind of thing is, in calculus, you may have to do something what's called a derivative or an integral of cotangent over cosecant. Well, derivatives and integrals are more complicated if you have to do them with fractions. So then it becomes a question, can we rewrite the original problem so it's not a fraction? And the answer is yes. You can rewrite the original problem as just cosine, and that's much, much simpler to work with than this. So that's the goal. This is usually the first step in a bigger problem in calculus, simplifying what they give you using trig identities. Okay, so we're not going to spend a lot of time on them right now, but there's just a few of them that we'll look at. Questions on it?
Cool. It's like a
Yeah, it's like a
substitution.
yeah, it's like substitution, and sometimes they even tell you, like in a really complicated identity, they give you the original problem, and they give you the final answer. So you have to figure out how to get to the final answer. In identities like this, they're really only 1 to 2 steps each. They're not going to do that. Some identities might be like 6 or 7 steps. So they start to get harder. All right.
Ooh.
Okay, so the homework, most of it's in the book. Okay, so it's a lot of unit circle problems and calculator questions. So you will need a calculator just to type in quite a few answers. And I'd like you to try simplifying one trig identity, and that's secant divided by tangent. Okay, so just try to simplify it as much as you can.
What do you mean? Oh wait, like
Change it to sines and cosines.
okay.
And see, so not everything cancels out. Sometimes nothing cancels out. You try it, and then you realize, well, I can't do anything with it.
Wait, alright, so if you have like 2 cosines on top of that, it'd be like cosine squared.
If you multiply a cosine times a cosine, that would be cosine squared. Yep.
Okay.